Next we'll look at the idea of tension, look at some worked examples to do with that. But first of all, tension is a force which exists when you join two objects together where one is pulling at the other. So for instance in ropes, if they're joining things, tow bars between a car and a caravan, couplings between train carriages, these are the kind of things that come up. And basically we can just apply Newton's second law in the exact same way that we've been doing, with one slight twist. So for instance, if I have a 3 kilogram block being pulled along by a 10 kilogram block with a force of 20 newtons. So that's our kind of situation. The tension will act in the join to pull this left hand block to the right, but that also has the effect of pulling back on the first block. So this is basically a Newton's third law pair, that the force that the 7 kilogram pulls the 3 kilogram forward is the same as the force the 3 kilogram pulls the 7 kilogram backwards. Equal force in opposite direction. But we'll revise Newton's third law in another chapter. But so what we can do now is apply Newton's second law, but the one slight twist is that we have the idea that we can apply Newton's second law to a whole system or to individual blocks within that system. The whole system has a mass of 10 kilograms and is being pulled along with a force of 20 newtons. The tension doesn't appear in that because it's what we call an internal force, and basically those pair of arrows would cancel each other out anyway. So, as usual, our method, draw a free body diagram, write an expression for the unbalanced force in that situation. And then you can use MA is equal to that, and then in this case 10 times A is 20, gives us the acceleration of the whole system. But if the system isn't falling apart, which we assume, then the individual parts within that system must have that same acceleration as well. So now if I look at the 3 kilogram block, the free body diagram for it, well, it's 3 kilograms, and it's being pulled, if we go back to the original diagram, it's being pulled by some sort of join, a rope or something like that. So the only force acting on it is the tension. There's been no friction involved in any of this. So in this example, Fun equals T, i.e. MA equals T. This time we know the mass, and now we know the acceleration. So we can rearrange to get the tension is 6 newtons. Now I could have got the same answer if I'd considered a 7 kilogram block, but it's a wee bit more complicated because it's got both the 20 newton force and the tension pulling it back. So it's always easier when you've got objects pulling another to consider the one being pulled. It's usually got less forces acting on it. The exact same logic though does apply to one object pushing another. So if I had the 7 kilogram pushing the 3 kilogram, the whole thing being pushed with 20 newtons, then I could get the exact same reasoning all the way through, deal with the whole system, get the acceleration as 2, and then when I came to dealing with the 3 kilogram on its own, what I'd have is a pair of Newton's third law forces at the force. If I call that A and B, it's probably a bit clearer. On object B, then what you've got is the force of the A pushing it. So you can work out that force between the two, just in the exact same way as we worked out the tension. Another common situation that comes up involving tension is the idea of a tethered balloon. So for instance, if you take a helium balloon which would be trying to float away and somebody's holding it in place, then the forces acting on it are what we call upthrust. I'll just label that with a U for just now. Basically the buoyancy force of the balloon. The balloon would have a weight, might be very small, but it does have a weight. But the key point for us really is the idea that the tension there's holding it in place. And if it's been held in place, then the forces are balanced, or the acceleration is 0 either way around. You get the same idea. And Fun is U minus W minus T. And if the forces are balanced, or the unbalanced force is 0, and we can set all that equal to 0, and then I can take T over into the other side, and I can say U minus W is equal to T. If I now cut the rope, then I'm getting rid of the tension. The bone will float away. That upthrust won't have changed. That weight won't have changed. But it'll now be unbalanced by an amount equal to the tension. That's what we've taken away from the situation. So that's now how unbalanced it's going to be. So now, with the tension taken away, the unbalanced force is equal to U minus W. But I don't actually need to know those values, because as we saw up above, that is equal to the tension that was tethering it before. So the unbalanced force when you release the tension is equal to the tension that was keeping it balanced in the first place. And you can now go and apply your MA is equal to T and solve for whatever you need.